Hey folks, Professor Gray here, ready to talk to you about estimates and sample sizes, and in particular confidence intervals in probability and statistics. Well, up to this point, we've mostly been dealing with descriptive statistics, statistics that describe populations or samples. In the real world, we usually know much more about a sample than the population, especially in the case of new research. Otherwise, why would you research it? Well, we're now going to focus on using sample data to form generalizations about populations, and that's called inferential statistics. We'll make inferences about an entire population based upon the sample data that we know. In inferential statistics, there are two major activities. One is to estimate values of population parameters, and the other is to test hypotheses about population parameters. And in this particular chapter, we'll talk about estimating values of population parameters. In particular, we want to be able to estimate the population proportion and the population mean. One way to do that is a point estimate. A point estimate is a single value, thus a point, used to approximate a population parameter. So we're only picking one value, 1 point. The point estimate for mu is x bar. If I only have one number to pick to estimate mu, population mean, the best number I have is whatever the sample mean is. The point estimate for sigma, that's the population standard deviation, is the sample standard deviation, S. If I can only pick one number, well then the sample standard deviation is the best one I have. And the point estimate for P is the population proportion. The best point estimate for that is P hat. Yes, P stands for population proportion P hat, that is the symbol for sample proportion. So P hat is the sample proportion. P without a hat is population proportion. Those are two new symbols. Here's an example. A Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. So let's find the best point estimate of the proportion of all adults that know what Twitter is. So for number one, we're estimating the population proportion. The best we can do is the sample proportion, 85%. So P hat is 0.85 or 85%. The problem with point estimates is that they're extremely limited, as you just saw. I'm just picking one number, one value to estimate a population parameter. Well, I could be exactly right or exactly wrong. And there's not a whole lot of wiggle room in between. So often statisticians will use an entire range of values to estimate a population parameter instead. Well, not only can we find this range, we can actually measure how sure we are of the estimate using probability. This range is called a confidence interval. It's a range of values used to estimate the true value of a population parameter. It's abbreviated CI. And it's kind of like this game on The Price is Right called the range game. And in the range game, you have a range that goes along a scale, and the contestant tells the range when to stop by pressing a button. And the idea is to get the range such that the true price of the car or whatever they're playing for is within that range on the scale. In a confidence interval, that's what we're doing. We're building a range that we are a certain probability or certain proportion confident that the true value of the population mean or proportion is within that range. Well, to construct a confidence interval, we need three things. The point estimate, which we just, in example 1, showed how to find. The confidence level and its corresponding critical value, and the margin. Well, we're going to talk about confidence level and how to find its critical value. The margin of error is calculated differently depending upon the type of interval you're making. More about that later. But the point estimate will be in the middle of our range, just as this depiction on the bottom of the slide shows. The point estimate is in the middle, and then the margin of error is the distance between the point estimate and the ends of the interval. What's our wiggle room? Here's a few words about confidence level. The confidence level is the probability that a confidence interval actually contains the population parameter. In other words, if I made these intervals over and over and over and over again, the confidence level is the probability that I will make an interval that actually contains the true population parameter, whether that's a mean or a proportion in our case. The complement of the confidence level is the significance level. That's denoted alpha. So for the following confidence levels, let's see if we can find the value of alpha. We can also define alpha as the total area in the tail or tails of the distribution that we're working with. But it is the complement of the confidence level. So in number 2, my confidence level, let's CL, is 0.90. So alpha is 1 minus that, because it is the complement, which is 0.10 or 10%. All right, number 3, the confidence level is 0.95. Alpha is the complement, so alpha would be 0.05 or 5%. Number 4, confidence level is 99%, 0.99. All right, then alpha is going to be 1% or 0.01. So alpha and the confidence level are complements. Well, we also need to know the critical values that correspond to the different confidence levels. Critical value is a number separating likely sample statistics from unlikely sample statistics. The critical value z sub alpha over 2 is a z-score, thus the z, that separates the area alpha over 2 in the right tail of the standard normal distribution. So alpha is the area in both tails combined, and in a confidence interval, the confidence level is the area in the middle of the distribution. So alpha would be what's left, and half of alpha is in each tail. The z-score on the right-hand side is the critical value. These will be important because they're used to construct confidence intervals. Let's do a few examples. We'll find the critical value z sub alpha over 2 for the following values of alpha. Number 5. Let's say that alpha is 10%. In other words, in my distribution, I've got area in the middle, and the total area, alpha, that's in the tail is 10%. All right, well, if alpha's 10%, 10% is in the tail, then 90% is in the middle because the total of the whole area under the curve is 1. Well, this also means that half of alpha, or alpha over 2, would be 5%, or 0.05. That's how much is in each tail. And what I want is the z-score, or the standard score, on the right-hand side. Well, this is actually like a Chapter 6 problem masquerading as a Chapter 7 problem. Because if I want to score and I'm given the area under the curve, I can find that using the calculator. I go to second bars, inverse norm, put in the total area to the left. Now be careful, I need the entire area to the left of the z-score, so that would be 0.90 plus 5% more, 0.95. 0.95 comma, the mean, 0, because it's a standard normal distribution. That's why I'm using z-scores or standard scores. 1 for the standard deviation, and I get my answer. Now, I'm going to round that to 3 places instead of the usual 2 for reasons that will become clear later. So the z-score, positive 1.645, is the critical value for a 90% confidence interval. Number 6 asks about what you get if alpha is 5%. Well, if I have 5% in the tails, then I've got 95% in the middle. And there will be 0.025, that's half of 5%, in each tail, since we split alpha between the two tails in this case. And I want the z-score again on the right-hand side. So I use my calculator. Second bars, inverse norm. Total area to the left of the z-score would be 0.975, that's 0.95 plus 0.025, comma, 0, comma, 1. And I get my answer. The answer is 1.96 rounded to 2 places. All right, now for number 7. This time, what if alpha is 1%? All right, here's a sketch. If there's 1% in the tails, that means there's 99% in the middle. Half of 1% be 0.005. Right, total area to the left of that z-score is 0.99 plus 0.005. So second vars, inverse norm, 0.995, comma 0, comma 1. I press enter, and there is my critical value. For reasons that'll be clear later, I'm going to round that to 3 places, but I'm actually going to incorrectly round it and do 2.575. And I'll show you why I'm going to do that here in a moment. If I take a look at my tables and scroll down to the positive z-score tables, down at the bottom right-hand side, you'll notice something interesting. Common critical values. I'll notice the common critical values that are listed here. Confidence level 0.90, 0.95, 0.99, critical value 1.645, 1.97, 2.575. Yeah, if I go back to the problems I just worked, 90% in the middle gives me a critical value of 1.645, 95% in the middle gives me a critical value of 1.96, 99% in the middle gives me a critical value of 2.575. So these are those 3 most common critical values that you'll come across. Occasionally, we'll need to use those critical values when you calculate things like minimum sample size, or if you're calculating a confidence interval with minimal calculator help using the formulas. Now note on the 2.575, why was that rounded incorrectly? Well, statisticians have agreed that empirically, what they have seen happen is that 2.575 is more accurate and occurs more often in real life. So that's why we appear to round that incorrectly. That's by convention. There are our 3 most common critical values. Well, to make a confidence interval, we need the point estimate, which we now know how to find. We need the critical values and the confidence levels, which we now know how to find. All that's left is the margin of error. A margin of error is the maximum likely difference between a point estimate, that's the center of the range, and the true value of the population parameter, and it's denoted with a capital E. The calculation of the margin of error depends on the type of confidence interval you're constructing. So there are different ways to calculate a margin of error depending on the type of confidence interval you are making. But the margin of error is your wiggle room. It's how much you are allowing in your range. And when we create the margin of error, we'll use the critical value from previously. And that inclusion of the critical value and the probability that it involves allows us to say that we have a certain level or percentage of confidence.